Today we'll learn instruction set of 8086 microprocessor. Most of the instruction has already studied in the previous lecture. The remaining part we'll discuss today. So 8086 microprocessor has arithmetic and logical instruction. In logical instruction, the first instruction is AND destination comma source. The AND destination comma source is the structure of 8086 microprocessor logical instruction, where the destination operand may be a register or a memory location, whereas the source operand may be a register, immediate data, or any memory location. Result is stored after AND operation in the destination operand. Some examples are here. Move AX, 3050FH, where 3050 3F0F is stored in AX, whereas 8008 is stored in BX. The AND operation will AND the contents of AX and BX, and finally they store the result in AX register. And instruction and operation we all know, but here are the rules related with AND operation. 1 and 1 will become 1, whereas 1 and 0 will be 0. 0 and 1 operation will result into 0, where 0 and 0 will result into 0. After applying these rules, AND operation will result into 3F, 0F and 0008. The AND operation will result into 0008H. This result will be finally stored into AX register. So the next instruction in 8086 microprocessor and logical instructions is OR instruction. In this OR instruction, we have a source and destination. The source and destination can be defined as destination may be a register or a memory location, whereas the source operand may be a register or a data or memory location. The result is stored after OR operation into AX register in the accumulator. So move AX 3F0F, and the contents of 3F0F will be copied or transferred into AX register, whereas the contents 0098 will be copied into BX. Now AX and BX are ready, then OR operation is applied on these two registers. After applying this OR operation on these two registers, the final result will be stored in AX, and the result will be 3F9F. The OR operation has got some standard rules. Those rules are: if we have 1 in a binary form and the 1 OR 1 will result into 1, the same way 1 OR 0 will result into 1, 0 OR 1 as a 1, 0 or 0 will be 0. If we apply those rules, we'll finally get the result into 3F9FH. In the logical instruction, we have next instruction as a NOT instruction. The structure of NOT instruction is NOT operand. So operand may be a register or it may be a memory location. The instruction inverts or it complements whatever the contents of AX register or the operand will definitely be going to be changed in some respective result, and that is related with the NOT operation. The examples are move AX, 0200FH. These contents are copied into AX register. After that, we'll get 200F into AX, and the contents of AX are complemented using NOT instruction, and the result we'll get is DFF0. we will see how the result can be evaluated. The NOT operation rules are, if we have 1 and we apply a NOT operation, it will convert it into 0, and if we have 0, binary 0, then that will convert into 1. With respect to that, the contents are 200F will be converted or complemented as a result DFF0H. The next logical instruction is test destination, source. Both operands in this instruction may be register, memory location, or immediate data. This instruction performs bit by bit logical AND operation for flags only. This will not result, or it will not generate any result in the accumulator or the respective register, but it will definitely reflect the result into the flags. If the corresponding 0th bit of the result contains 1, then the result will be non-zero and 0 flag will be cleared. That means it will be 0. If the corresponding 0th bit of the result contains 0, then result will be 0 and 0 flag will be set. The example for test instruction is test AX, BX. So it will work on these two operands as it is defined. The operand can be memory, then this is a 0500 is the memory location on which the contents 06 are applied for test operation. Next we will learn about shift and rotate instruction. These instructions are mainly used for using the contents of a data. Sometimes we have around 8 bit of register. So this register will hold 8 bit of data from D0 to D7 contains. These bits will have to be rotated many times for getting access of a particular bit. Sometimes we need to know what is there in the third bit of that particular data, so that we need to get access of that, and that will be done by using shift and rotate instructions. So we have many shift and rotate instructions. Some are here. SHL is a shift, this is a shift logical left, or it can be shift arithmetic left. Then we have SHR, shift logical right, SAR, shift arithmetic right, ROL, rotate left, ROR, rotate right, RCL, rotate left through carry, RCR, rotate right through carry. So we'll see it one by one. The first instruction is SHL instruction. This SHL instruction performs a logical left shift on the destination operand, filling the lowest bit with 0. So whenever we shift, the shift will be in the left direction as it is defined. So whenever we shift it bit by bit, the D0th bit will be shifted, or the information at 0th bit will be shifted to D1th bit, and D1th bit information will be shifted to D2 and so on. But this D0th bit will get a 0, the additional 0, and this is how it rotates. The example for this instruction is SHL register, the name of a register, and immediate information or immediate data. SHL memory can also be used for in this instruction. Then SHL register and CL. CL will contain the information with which the SHL will work. Here is the fast multiplication which will be offered, or which will be done using a shift instruction. Shifting left one bit multiplies a number by 2, because if we have an information like this, then 0 0 0 0 0 1 0 1, it means 5 as a hexadecimal format, and this is in a binary format. But if we shift it by 1, so we will definitely get a 0 value, 0 information at the D0th bit, and all these bit will be shifted. After shifting these bits, we'll get the information as a 0 0 0 0 1 0 1 0. It means 10. So what we got is the multiplication of the number by using shift operation. So shift operation allows us to calculate the multiplication just by shifting the information. So just by shifting the information left by 1 bit, we'll get the number multiplied by 2. So for example, here if we move contains 2 here and shift the contains by 2, so we are shifting the contents by 2. By shifting the contents by 2, it means 2 to the power 2, and the number shifted is 5. So we'll get 20 as a result in the final destination. So this is an example. With this, we can shift the contents and get the multiplication after shifting. The next instruction is SHR instruction. The SHR instruction performs a logical right shift on the destination operand. The highest bit position is filled with 0. So as if we were in previous instruction, we were shifting the bit to the left, here we are shifting the bit to the right. So the D0th bit will be shifted, whereas D1 bit will be shifted to D0, but in D7th bit we will get additional 0 and all the contents will be shifted to right. This is how when we shift the content, this is a carry flag, so the contents will be moved to carry. Then move DL comma 80, 80 is the information. Shifting right n bits, it divides the operand by 2 to the power n. So if we move the, for example, if we move the contents 80 into DL, SHR is shifted by once and then SHR is shifted here by twice. If we shift the contents by 1, so we will get the contents 40 as a result. It is nothing but a division by 2. The same way, if we shift the content twice, then again a division and we'll get a result as a 10. Then we have SAR instruction, shift arithmetic right, performs a right arithmetic shift on the destination operand. The arithmetic shift preserves the number's sign. We all know that the sign number will be represented in D8th bit, and it will remain as it is, but the contents will be shifted. Here we are not adding a 0, additional 0 will not be added, but the sign bit will continue to remain same in the D7th bit. That's why we always get the signed result finally in the destination, and the sign number will be copied or transferred from left to right because we are applying a shift operation. The arithmetic shift operation preserves the number by sign. If we apply 1, then it will divide by 2 and will get a result as a minus 40. The sign number will always be maintained in this particular instruction. RCR. This instruction rotate through carry. The carry information will be a part of this particular instruction whenever we are rotating the contents in a particular destination register. Each binary bit of the operand is rotated towards right by 1 position through the carry. Least significant bit LSB, that is B0, or we can refer it as a D0, is placed in the carry flag. The carry flag bit is placed in the most significant bit MSB position, that is B15 if we are applying on 16-bit register, or if we are applying on 8-bit register, it will be B7. So this is example. How does it work? So if we are trying to shift the contents, RCR through write through carry. So the contents of carry is 0 and the contents at B0, B1, B2 are likewise. So when we move the contents will be moved into the carry flag. So this B0 contents will be shifted to carry flag, and the contents of carry flag will be shifted into B15th location. This is how it works. The contents are copied, and after rotating we will get the contents of B1 into carry flag and the contents of carry flag into B15. Then the next instruction is rotate left through carry. So when we try to rotate the content through carry, as we have done in the previous instruction, the same will be applied, but here we are rotating left side, but carry flag will be a part of this rotation. Each binary bit of the operand is rotated towards left by one position through carry flag. Least significant bit LSB of an operand, that is B0, is placed in B1 and B1 into B2. The most significant bit MSB of the operand is placed in a carry flag. Here the contents of B15 will be shifted into carry, and whereas carry flag will be shifted into B0. This is how it rotates, and after rotation we will get the contents like this. See, the contents of B15 are copied into carry flag, and it's not copied, it is transferred, and contents of carry flag, it was 0, has been shifted to B1th location. Then ROL instruction, rotate, shift each bit to the left. So here what we are trying to do, we are rotating the information, but we do not consider the carry flag as a part of rotation. The highest bit is copied into both carry flag and into the lowest bit. So this is the highest bit, it is a D15th bit in case of 16-bit information, D7 bit in case of 8-bit information. So this, when we apply this ROL instruction, the contents at B15th bit will be copied into B0 bit, whereas the same contents are moved or copied into CF flag or carry flag. So example is move AL. So this AL will have the contents, 8-bit contents like this. Then ROL, rotate it once. So once we rotate, the D15th bit contents will be moved here into B0th bit and carry flag will be set definitely. Then move DL, 3F will result, for rotating 4 times, will result into F3 as a final result. Then ROR instruction. ROR instruction is same as the previous instruction, but here we are rotating the contents into right direction. So during this we are not again using the carry flag for rotation, but the information will be transferred from lowest bit into carry flag. So move AL, this is the example, 1 1 1 1 0 0 0 0 are the contents. If we rotate right it for once, we will get the contents of this information into the B0th bit will be moved to B1 bit and carry flag will be reset because it was having 0 at B0th location. If we move the contents CF into DL flag and we rotate it 4 times, then F3 will be the final result. This is how we understood the details related with the rotate and shift instructions used in 8086 microprocessor. The remaining part of the instruction we'll see in the next lecture. Thank you.